So my name is Miriam, and I'm a PhD student at Princeton University, and I'm going to be presenting work on symmetries and fairness in multidimensional mechanism design, and this is joint work done with Matt Weinberg. So I'm going to start with the motivation. So we consider a revenue maximizing seller with multiple items for sale to a single population of buyers. We are looking at auctions where buyers represent advertisers and items represent users and views from demographics. So what do we mean by items represent views from demographics? So the way you should think about this is an auctioneer has a lot of data on users, and an advertiser can submit a bid based on data profiles of users or demographics of viewers. So we're going to motivate this direction via fairness in ad auctions. And there is a classical definition of fairness here that is used in prior work, which is that equally qualified users from different demographics should see the ad at equal rates. So what this means is that if an advertiser places an identical bid on two users from different demographics, then those two users from two different demographics should view the ad with the same probability. And this is relevant in ads for housing, employment, etc., where biases can be illegal or unethical. So advertisers are going to specify budget preferences and place bids for different user demographics. For each user, an auction is going to be carried out by the seller to determine the price of their slot. And one obvious reason that could cause unfairness if its ads are discriminatory. So for example, if an ad values two users equally but places different bids, that's obviously going to lead to discriminatory outcome. But recent work shows that even when ads are fair, discrimination can still happen. So even when ads individually place equal bids on users that they value equally, the allocation can still be unequal and it could still lead to discrimination. And we're gonna illustrate this with an example next. So in this example, we have two items. So item one is female users, item two is male users, and we have two bidders. So buyer one here is STEM jobs, and buyer one is going to bid one for female users and one for male users. So they're not discriminating against either users. But we have a second buyer here, which is maternity clothes. And this advertiser here is going to bid two for female users, but nothing for male users, so zero. And so in this setting, the seller is going to try to maximize their revenue, so they're going to run a second price auction. The second price auction is, there's nothing unfair about a second price auction, but the result of this is the second buyer is going to get this item. So female users are only going to see maternity ads and no STEM job ads. And the first seller is going to get this item. And so male users are going to see the STEM job ads with probability 1. So as a result, the female user demographic is not going to view any STEM job ads, while the male user demographic is going to view STEM job ads with probability 1. And despite the fact that the STEM job ads bid in a non-discriminatory manner and bid 1 on both users, and despite the fact that the auction is fair because it's a second price auction, the result is going to be an unfair outcome. And so that's going to be a problem. So in this example, which appeared in a lot of prior work, we show that even though STEM jobs are fair, outcome is unfair. And this is because the first ad, STEM jobs, does not target based on demographic, but the second ad targets female users. And so this creates competition for female users. And this leads to imbalance in the platform because a lot of advertisers are going to want these slots and the price for this is going to be higher. And so STEM jobs are not going to win any slots for female users. And so discrimination happens inevitably. So platforms, as we just saw, platforms suffer from various spillover effects due to competition. Discriminatory outcomes accentuate pre-existing biases even when the ads behave fairly individually. And in the example we saw, even if the STEM jobs are fair, the outcome is unfair for female users. And prior work studied worst case settings, designed auctions for those settings, and found impossibility results. But what we are going to do is we're going to focus on population level information. and problems instead of worst case. I'm going to show an example later to explain what I mean by population level, but first I'm going to present the model. And this is the setup. We have n buyers, so n ads or n populations of ads. So this could be STEM jobs, this would be maternity clothes, this would be men's shoes, etc. And we have m demographics, so m items, and each item corresponds to a user demographic. So this could be female users, this could be male users, and so we have m type of them. And add i's value for demographic j is represented by this distribution vij, and di here is the product of the dij's, and it represents the ith population of ads. And the way you can think of this is, for example, if this corresponds to STEM jobs, then you have like 1 million different STEM job ads, and when we're running an auction, one of them is going to be present and bid on this particular auction. And the way we present the population of buyers is D, which is the product of the DIs, and this is going to represent the entire buyer population. So we have n buyers, m items, and D is the population of buyers. And okay, so the way the auction works is that some user from some demographic J is going to visit some page. And when they visit that page, then we draw a value for each of these ads from their respective distributions. And so the seller is going to get n values, one from each advertiser type, one from each population of advertisers. So for demographic J, it's going to be like V1, V1J, V2J, Vij, all the way to VNJ. And the seller is going to look at these values and decide an allocation and price for this user slot. Oops. For this user slot. And the goal of the seller is to design a truthful mechanism that maximizes their expected revenue. So this is the model setup. So now we're going to look at another example to explain what we mean by population level. If you consider the following example, we have 2 items and 3 bidders. Item 1 represents the demographic of female users. Item 2 represents the demographic of male users. Here we have buyer 2 is STEM jobs, or it represents the population of advertisers for STEM jobs. Concretely, their value is going to be 1. It's going to be a point mass 1 for male users and female users. So STEM jobs are going to have value 1 for this demographic of user and value 1 for this demographic of user. On the other hand, we have buyer 1, which is going to be the population of advertiser for maternity clothes. And in this case, D21 is equal to 2 with probability 1/2 and 0 with probability 1/2, and D22 is 0 for the male users. Concretely, what this means is that half of the maternity clothes advertisers are going to have a high value for displaying their ad to women, and half of them are going to have no value to displaying their ad to women. And all of the maternity clothes advertisers have no value displaying their ad to male users. And the third buyer is men's shoes. And this buyer has the opposite of what maternity clothes has, which is they're going to have a high value for displaying their ad to men, which is 2, with probability 1/2 and 0 otherwise, and no value for displaying their ad to women. And in this case, if you look at the population level information, and if you run an auction on this, in expectation, the STEM jobs are going to be, the STEM ad jobs here, the second buyer, is going to be displayed to female users with probability 1/2 and to male users with probability 1/2. And so this example here is still fair at the population level. And this property was not captured by the previous definition of fairness. So we're going to introduce a new definition of fairness that captured this, and we're going to call it interim fairness. And the way interim fairness is defined is an allocation is interim fair if when some user from demographic A is valued higher by some user in demographic B, then user from demographic A sees that ad at least as often as demographic B in expectation over the other bidders bid. So the difference is that we're not looking at worst case scenario now, we're looking at Bayesian settings, and we want things to be fair in expectation over the population of the buyers. And more than just interim fairness, we're going to also study a stronger definition of fairness here. So recall in the prior work that we saw, the fairness guarantees that was demanded was that equally valued users are shown an ad with the same probability. But here we're going to do something stronger. And we are going to demand that if a demographic A is valued higher by an advertiser than some demographic B, then users from that demographic are shown that ad at least as often as those from demographic B. So we are going to call this strong monetarity in fairness. So this leads us to our main question. So required an auction to satisfy these constraints that we saw, interim fairness and strong monetarity in fairness, is going to limit the auctioneer's ability to optimize its revenue. And we want to study the trade-off between satisfying those constraints and optimality. And that's going to lead us to our main question here, which is for additive buyers with independent values, what are the guarantees of fair, simple mechanisms? And we're going to focus on a subset of mechanisms that satisfy interim fairness and strong monetarity in fairness, which are symmetric auctions. And symmetric auctions are anonymous and unchanged in their permutation. So whenever a bidder or an ad swaps their bids for two items, they swap the probabilities with which they receive those items too. A simple example would be if we had STEM jobs submit 1 for female users and 10 for male users, and then the seller gives them female users with probability 0.1 and male users with probability 0.5, then if they were to flip their bid and instead submit a bid of 10 for female users and 1 for male users, then that should automatically swap their allocation probabilities, and they should get 0.5 for female users and 0.1 for male users. And this is fair by definition. This is fair by definition. Because whenever a bidder swaps their bids, that swaps the probabilities, and so it's anonymous. And not only is this fair, but it's also strongly monotone in fairness. And in particular, we're going to look at a simple symmetric mechanism, which is BREV, which sells the users as a bundle. And in this auction, the auctioneer does not use any personalized data at all and displays an ad to whatever user shows up independently of their demographic. So this is a symmetric mechanism, and it's a simple one because all it does is ignore data completely. And our main result is going to be that this BREV auction is going to be a constant approximation of symmetric opt. So for a single population of additive buyers with independent item values and any number of independent items, bundling the items together, which in this case corresponds to just concealing all demographic data and treating all users the same way, is going to achieve a constant factor approximation to the revenue optimal item symmetric auction. We also have a bunch of other results that I'm not going to mention now, but they improve this constant approximation here. And the main idea is that if you insist on running a symmetric auction that satisfies strong monetarity and fairness and interim fairness, then you can almost do as well as the symmetric opt if you just ignore all data. And so we conclude now by just recapping what we just saw. So we first proposed a relaxation of this we first introduced a new measure of fairness for Bayesian settings, which is interim fairness, which guarantees that things are fair in expectation over the population. And we focused on symmetric auctions because they are strongly monotone in fairness, and that is a stronger guarantee than the previous definitions of fairness that we studied. We showed that fairness constraints are satisfied at a constant loss of revenue within the context of symmetric auctions. So what we showed is that a simple symmetric auction that we call BREV satisfies these fairness constraints and at only a constant loss of revenue. But the next step that would be interesting was would be to see what the revenue guarantees are within the broader class of mechanisms that are strongly monotone in fairness and not just symmetric, because symmetry is a stronger constraint than strong monetarity in fairness. Yeah. So yeah, that's it.
Okay, great. Thanks, Miriam. We have a minute for questions, so please do drop your questions in chat or the Q&A. One initial question would be, can you talk more about some of these next steps that you mentioned? What are some first challenges or refinements that seem promising to you?
So for this last question here, it's harder to define the broader class of mechanisms that is strongly monotone in fairness. So I guess an interesting thing would be to try to find auctions that are not symmetric, but that are still strongly monotone in fairness, and see what the optimal, like how well you can do within that class, and then compare BREF to that, or try to come up with an auction that is not necessarily symmetric, but that does better while still satisfying strong monotonicity and fairness. Does that answer your question?
Yeah, thanks.
Okay, so we had this stronger definition of, we had this fairness definition here, but then we focused on mechanisms that were a subset of these, of the auctions that satisfy this. And so like the next step would be to just consider the broader class here. And a hard part about that is just defining those mechanisms and finding the optimal one among these mechanisms.
Okay, great. Thanks, Miriam.